This tutorial is meant to give you additional information related to the separation of mixtures. The important thing to keep in mind when we're trying to separate mixtures is to understand and then to exploit the differences in properties between the components in the mixture. So those properties that are exploited might be chemical in nature or they may be physical in nature. Now, the choice of whether we choose to drive the separation using chemical or physical properties will depend on the outcome that we're looking for. So if we're looking to isolate the components of the mixture and have them be the same before and after the separation of the mixture, meaning chemically the same, then we would want to resort to physical properties primarily. On the other hand, if we don't necessarily mind that the identity of the components might be changed by performing a chemical reaction, then we might be able to resort to chemical properties instead. Now, when it comes to understanding what our options are, in general, usually if we're trying to separate mixtures, we have a couple, or I should say four specifically, techniques that we can use to carry out the separation of mixtures. Now, one of those techniques would be filtration or decanting. The other is crystallization. Yet another would be distillation and solvent evaporation. And lastly, it's also common to use chromatography to separate mixtures. And we'll be discussing each of these in turn in the rest of this tutorial. So if we're going to be using, say, filtration or decanting to carry out the separation of a mixture, well, really that works best for those mixtures that are heterogeneous in nature, meaning, like for example, in this particular picture that I'm showing you here, essentially what we've got is two mixtures in separate beakers, and in each beaker we have a liquid layer that's sitting on top of a solid layer where the solid component is settled out to the bottom of each of these containers. And so here, the difference in property that we're looking to exploit is actually the difference in physical state. For each of the components in the mixture. And so essentially, all that we would do to separate this type of mixture is we would basically just go and set up a simple filtration apparatus where we have a funnel, and within the funnel we have folded or fluted a piece of filter paper, and that's actually set up on top of an Erlenmeyer flask that's meant to be the receiving flask. And so you would pour this mixture that has two phases into it, and the liquid phase would filter through the filter paper and the solid would be trapped on top of the filter paper within the funnel. And so that's a very simple way to drive a separation for a mixture that has two separate phases. It is also possible to use a technique called decanting. Basically, if we have a mixture that's separated out like this, then it could be possible just to pour off the liquid layer in each of these, and if we're careful enough, we can trap the solid behind in the beaker. Now, this technique also happens to work if I actually have two distinct layers, even if they happen to be liquid layers. In which the liquids have separated into two distinct layers, say like oil and water. I could actually pour off the oil layer first, trapping the water layer behind in the original beaker and having the oil layer in a new beaker that I've decanted into. And so that's another way to actually drive a separation in terms of manipulation of liquid layers. Now, another potential technique that we could use is something called crystallization. And here, the property that we're looking to exploit is actually a difference in solubility, or the ability to be dissolved in the solvent involved in the mixture. So suppose, for example, in this picture up on top, suppose that I have two components that are dissolved in water, and one of those components dissolves really, really well in water, but the other one doesn't dissolve quite so well. And so what I could do is assuming that the component that does not dissolve in water is in a high enough concentration in the mixture, I could try and provoke a crystallization. Now, there are a couple of ways to do just that. Basically, one way to do this, some of these crystallizations happen so readily that they can't occur at room temperature, though they often need a little help. The way that you provide that help is by introducing something called a seed crystal. And usually that's a small, tiny grain of the original component that's in relatively a pure form, and you go and you drop it into the solution, and you're hoping that by adding that seed crystal, what's going to happen is that this component that's in such high concentration that it's going to find that seed crystal to be a perfect surface on which to start creating more of that same crystal. And so eventually, if you do that, then basically you get a network of these component crystals starting to form within the solution. And basically, you would just go and pour out the remaining part of the mixture if that crystallized component is what you're looking for. It is also possible to assist components in terms of being crystallized out of a mixture if you actually run the crystallization at low temperature. Low temperatures also tend to favor the formation of crystal lattices for reasons that we'll discuss later in the year. Yet another technique that we spoke about briefly at the start of the tutorial is this technique of distillation. Now again, as the notes here on the slide tell you, essentially the property that we're looking to exploit here to drive this separation is a difference in boiling point. So to sort of take you through that process so that you understand more or less how a distillation process works, I want you to pay attention to this mixture in this round bottom flask. Now let's suppose that this mixture happens to be composed of water, which has a boiling point of about 100 degrees Celsius, and suppose it's also composed of hexane. All right, and hexane has a boiling point of about 68 degrees Celsius. Now, in that instance, this mixture would be colorless because hexane is not a colored substance and neither is water, but this is just a quick example to sort of help you understand more or less how the process works. If you take note, there's a thermometer located in the apparatus right there. And essentially what we would do is we would take this water and hexane mixture and we would go and heat it up. And as the mixture heats up, if we're paying careful attention to the temperature readings, once we start reaching 68 degrees Celsius, what's going to happen is you're going to notice that you're going to get the formation of a vapor. Right? That vapor would be hexane vapor. And notice that the glass apparatus is set up so that essentially this thermometer is sitting pretty much in a solid glass stopper. So essentially there is no way for this hexane to escape rising through the top of the round bottom flask. The only other place for this vapor to go would be this way, through the side arm of the apparatus. Now this side arm is called a condenser. All right, now a condenser has this outer jacket, all right, that actually has tubing connected to it. This tubing comes from sink and a faucet. And basically what you have is you have water actually running through the outer glass jacket of this condenser. And what that does is it creates a colder environment so that once this hexane vapor hits that colder environment, it re-enters the liquid phase and pours down into the receiving flask. And so once all of the hexane has completely evaporated from the round bottom flask here on the left, and it has re-entered the liquid phase and resettled in the receiving flask on the right, then basically the hexane would be in this flask and the water would be left by itself on the round bottom, or in the round bottom flask on the left-hand side. Again, provided that we're careful and we don't allow the water to reach 100 degrees Celsius, then basically the components would remain separated. Obviously, if we're not careful and we let this continue to heat, then eventually the water would also do the exact same thing as the hexane and it would vaporize and eventually travel over into the right-hand side flask. Now again, normally if we carry out the separation successfully, then essentially what we should get is the separated component, known as the distillate, and the original component that it was mixed with still in the original flask on the left-hand side. Another technique, and one that's actually used quite frequently in industry, is chromatography. Now here, the difference in property that we are looking to exploit would be differences in the attraction to a solid support. What I mean by that is, say for example here, in this picture that I've included in the tutorial. What you have here is an outer glass chamber, okay, and within this outer glass chamber, there's a strip of paper that I'm outlining in green, and within the very bottom of the chamber, there is a solvent, which I'm highlighting in blue. Essentially, the way that this works is the mixture that you're looking to separate. In this case, we're separating ink from different black markers. So, for example, this black spot right here, that's your mixture that you're trying to separate. And essentially what's going to happen is you're going to get the solvent moving up the strip, and eventually once it touches that spot of your black ink, it's going to go and start to make that ink run. As you're able to see right here, you're starting to see that spots start to separate. And eventually what's going to happen is you're going to see the different colors start to come out. Like for example, there's purple down at the bottom of the smear, if you will, and then here's sort of a light blue at the top of the smear. And the way that this works is essentially the purple ink stayed at the bottom because basically it was attracted most to the paper as compared to the other inks that were in the black marker ink, and it was attracted least to the solvent. All right, now if you take a look at this blue spot, then the blue spot, what we can say is it was attracted to the paper, but attracted most to the solvent. Okay, so because of that attraction to the solvent, the blue ink traveled much farther up on the paper, all right, as compared to the purple spot or the purple ink that barely traveled at all, because the purple spot was actually attracted much more strongly to the paper and attracted less so to the solvent, which meant less migration up the paper test strip. If you'd like to actually explore this a little bit more, this technique, and sort of understand it, this is a great simulation that you can use. Just quickly show you what's involved. Basically, you have this similar setup that you're seeing, except now that your test mixture is actually green instead of black. Essentially, what you can do is you can change the parameters, all right? And what you're going to find is the more different you make these parameters, then the more separation you're going to achieve. So I would encourage you to play with this simulation a little bit, just so that you understand more or less what's involved. If you see, basically we've increased the solubility of the blue pigment in the solvent, so notice that the blue pigment travels farther up the paper as compared to the yellow, which has less solubility in the solvent, and so as a result it travels less on the paper. So that's pretty much separation of mixtures in a nutshell. When we come into class tomorrow, you'll be given an activity where you'll have to apply these concepts. If there are any questions, by all means, please let me know.